Hello dear DP and other physics students, welcome back to Rubber Duck Physics. In the last video, we discussed why studying relativity can feel so counterintuitive and how Einstein's revolutionary ideas turned 18th and 19th century physics on its head. Today, we'll step back to something a little more familiar and intuitive, Galilean relativity, and explore how it lays the groundwork for Einstein's ideas. Let's begin with defining a few concepts we will need to describe relativity. A reference frame is a mental tool that helps us measure the position of objects in space and time. Mathematically, it's a coordinate grid with an origin and scaled axes plus a clock. To describe physical space, we need three coordinates, usually x, y, and z. Observers are stationary within their own reference frames. For example, this duck here is our observer. The duck doesn't have a given position. View it rather as an official. Commissioned to run the whole reference frame, it sees itself as stationary and measures everything else as moving relative to it. An event is a single, instantaneous occurrence, like this chick hatching from its egg. In our duck's reference frame, we can describe the event's coordinates as x equals 5 meters, y equals 0, z equals 0, and t equals 4 seconds. All events are observable from all reference frames, but different observers might assign different coordinates to one event, depending on their position or motion. Let's clarify an important idea. Physics doesn't work the same way in all reference frames. Newton's laws are valid only in inertial reference frames, those that are not accelerating. If a frame accelerates, like inside a turning car, a rocket taking off, or a falling elevator whose cable has just broken, object velocities appear to change without any net force acting on them. In an inertial frame, however, every acceleration is caused by a resultant force, as Newton's second law states. This means inertial frames are the foundation for describing motion in a way that's consistent with Newtonian mechanics. To deduce our relations of finding coordinates measured by different observers sitting in their different reference frames, we start with two reference frames, and we can make some simplifications. First, clocks in both frames start at the same time. Second, their axes point in the same directions. Third, their origins coincide at t equals 0. And finally, the frames move relative to each other only along one axis, let's say the x-axis. These assumptions make it easier to understand transformation between frames without losing any generality. Let's look at the chick's coordinates from both reference frames. In the duck's frame, the chick is stationary, so its position doesn't change. In the bunny's moving frame, with the dashed axis moving at velocity v with respect to the duck's one, however, the chick appears to move to the left. To find the coordinates in the bunny's frame at any time t, we use the equation x dash equals x minus vt. To transform back, the bunny can use x equals x dash plus vt. Now imagine the chick starts walking to the right at 0.5 meters per second. From the duck's perspective, its velocity is simply 0.5 meters per second. But in the bunny's moving frame, we calculate the velocity as u dash equals u minus v, which is 0.5 minus 2, giving us negative 1.5 meters per second. The chick appears to move backwards. You have definitely seen this if you have watched a runner or biker from a quickly, uniformly moving train. This is Galilean velocity addition. The bunny can reverse the transformation by rearranging to get u equals u dash plus v. Here is why this is important. If we calculate accelerations from these velocities, the constant v cancels out. Both the duck and the bunny observe the same acceleration, meaning Newton's laws hold true in both inertial frames. This is the Galilean Newtonian principle of relativity. The laws of mechanics are the same, or, using a word we just love when discussing relativity, they are invariant in all inertial reference frames. This leads to an important conclusion. In the universe, there is no special location, no special direction, and no special speed. There is no absolute reference frame at rest, no highlighted inertial frame. All inertial frames are equally valid for describing motion, and the laws of mechanics hold true in all of them. I hope the question of my last video is coming to your mind. No, there is no way you could tell if your bed is in your bedroom or in a hurtling spacecraft if the vehicle is not accelerating anymore. No way to tell if you are moving or stationary in an inertial reference frame because the laws of mechanics work the same. Galilean relativity works well for everyday speeds, those we experience intuitively in our daily lives. The movements of objects like a ball rolling, a car driving, even a space rocket flying match our expectations because they align with our intuition built from countless interactions with Newtonian mechanics. But as we'll see, when velocities approach the speed of light, intuition begins to fail us, and a new framework is needed to explain motion and forces. That's where Einstein's special relativity comes in. Before the next video, please think, what if you, now pranked by your two funny friends, flash an emergency light signal back to Earth? If the spacecraft is moving at 30 km per second relative to Earth, and the speed of light is 300,000 km per second, how fast would that light signal appear to travel for those receiving it back on Earth? We'll explore this surprising answer in the next video. Let's summarize what we have learned today. A reference frame is a tool to describe the position of objects in space and time. Inertial reference frames are those where Newton's laws hold true and they don't accelerate. Observers in different inertial frames will measure different coordinates for the same event, but the laws of mechanics are invariant in all inertial frames. The Galilean transformation describes how coordinates and velocities change between inertial frames. Galilean velocity addition explains why objects appear to move at different speeds depending on the observer. These principles align perfectly with our intuition about motion in everyday life, but they begin to break down when speeds approach the speed of light. Before we wrap up, let me tell you that I am also available to tutor students in physics and maths at the high school level. If you are studying A-level physics or maths, AP physics, IB/DP physics, or a similar level subject, and you would like extra support, I am happy to help. To contact me, you can find my email address in the channel data of the Rubber.Physics YouTube channel. Just a quick note, it's visible only if you are using a browser on a computer. Feel free to reach out if you would like tutoring tailored to your needs. I would love to work with you. Thank you for watching Rubber.Physics. See you next time.